Hello, guys. Welcome back to Math Zone African Motives. We are still on our grade 12 mathematics, and this is a continuation. We are going to consider an application of our derivatives, right? So this is going to be application of our derivatives. And also, we are going to consider, in our case, we are going to also consider the factorization of the cubic polynomial. So that's another application again when we had our cubic polynomials, remember from our previous classes that we had. So those two applications, we are going to try by all means to apply them in the sketching of the cubic graph. That's the cubic function. If we are to consider the cubic graph, it is simply taken from our cubic polynomial. All right, so we are simply saying here, I want us to have the basic understanding. A cubic polynomial, let us have this one, is a function, actually. It is a function of the form f of x is equal to ax cubed plus bx squared plus cx plus d. This is what we had. So in order for you to sketch the graph, just like when you had a quadratic, remember we dealt with a quadratic graph before. Given our f of x is equal to ax squared plus bx plus c, you had to consider a in terms of what? The shape, where a is greater than 0, considering positive values. All right? We are going to have our graph being what? Concave up for a quadratic. Where a is less than 0, we're going to have our graph being what? Concave down. But as of a cubic function now, all right, as of a cubic function, the a that we are going to consider as we are considering our cubic function, remember, in our case here, a is not supposed to be equal to what? Is not supposed to be equal to 0. So if we are going to have our a greater than 0, it is for the shape now. That is what? For the shape of our cubic function. When a is greater than 0, talking about what? Positive values. We can have our cubic function like this. So this is the shape that you're going to have of a cubic function for a is greater than 0, where in our case, we have got two turning points. For this one, there are two turning points or stationary points. It can be a condition of something like this, where it is at what we refer to as the stationary point of the point of inflection, or it can be just something just like something like this, where we do not have the turning point at all. It is the shape that is where a is greater than what? Greater than 0. This is what? The shape. On a condition where a is less than 0, we can have, in our case, this time it's going to be like this, going down, all right? So this is the case where a is less than 0, and you're going to have two turning points, all right? Or it can be something like this, all right, where it is having the stationary point of inflection, or it can be something where you actually do not have a turning point at all. So here it's going to be two turning points, one turning point, all right, two turning points, one turning point. So with this shape or from these shapes, I'm going to consider match on this one where you have got what? 2 turning points. That's the most case that you're going to have. Yes, you can have any of these, but let us consider much about that. All right. In any of the cases, I want you to see something here. If let's say this graph was drawn, I'm considering a basic graph that we can have of a cubic function, a basic one that we can have. It is supposed to be having, all right, this shape or this shape, any basic. With the 2 turning points, let us say we've got something like this. There's a turning point there, then another turning point like this. All right, this is our cubic function. I just want us to see something. Major properties that we are going to need in order for us to have this sketch. One, we can see that the shape is being applied. Two, this graph crosses or passes through the x-axis. Just like a quadratic graph that we had before, where it crosses or passes the x-axis, those are your x-intercepts. Nothing has changed on our cubic function. This point, this point, this point in the x-axis will be our intercepts. That will be our intercepts, our x-intercepts. So we need those x-intercepts. Then we have got the y-intercept where the graph crosses or passes through the what? The y-axis. Remember that condition. So we've got what? The y-intercept. For this graph, you are going to notice that it will be having 2 turning points, or it can have 1 turning point like this one. But as for this sketch, there will be a turning point, a turning point. These are stationary points or turning points, right? That's a turning point, and this one also be a turning point. So we have a turning point and a turning point. So remember, the turning point of a graph can actually tell us like how the graph is, like how the function is given from the sketch that you have. You can tell from the turning point to say, all right, let's consider here from this point up to this point. The graph is what? Increasing. That is what? Going up. From the turning point here like this, the graph is what? Decreasing, going down. From that, it is going what? It is going up. The turning point can actually help us to consider whether from that point, the graph is increasing or not from the turning point. All right, like this, it is a decrease. From this turning point, because that turning point is a stationary point, meaning to say there is no movement at the turning point. So from the turning point going up, it's now an increase. All right? From this turning point like this, going down, a decrease. From here to the turning point, an increase. So this is the condition of the turning point. It helps us actually to determine that part of what? Increase or a decrease. And remember, from our derivatives, when we had our derivatives, we talked about the turning point, a stationary point. At that turning point, we saw that the first derivative is supposed to be equal to what? It is supposed to be equal to 0, meaning to say derivatives can be applied when we are to consider anything about the turning point. Derivatives can be applied. All right, I'm going to write the notes about that. All right, but for now, that is something that we can actually consider. The derivatives cannot be applied when you consider the turning points. The x-intercepts, guys, is as before. These x-intercepts as before, because it is in the x-axis where y is equal to 0. So you simply have to consider your f of x to be what? Equal to 0. Your cubic function that or whatever that you have from the equation, you consider that to be equal to 0. Meaning to say, in order for you to solve this, you must go back to the factor theorem now, where you have to consider those long division, synthetic division, or by inspection, where you are supposed to factorize the cubic, equate to 0, find the values of x. Then for the y value, the y-intercept, simply the constant d. When y is equal to what? I mean, when x is equal to 0, your y will be equal to d. That will be your y-intercept. So that part, it is direct. We are going to talk about that in our calculations, but I'm gonna list the notes like I said before. But this is the major property that you're going to have for you to have the sketch. You are going to need the turning points, x-intercepts, the y-intercept, and there is another one which is to be added. We never had that on a quadratic function. We never had that part, which is referred to as the point of inflection. We never had it on a quadratic, but on a cubic function, there is another condition referred to as the point of inflection, which is to be applied from our second derivatives. It follows that for the second derivative with respect to x to be equal to 0, you will be having a point of inflection. A point of inflection is the one that can tell us whether the graph from that point, whether the graph is concave up or down. All right, let's consider like this. From our graph that we have here, I want us to see something. I'm going to talk about this, do not worry. It follows that, let's say we have got that second derivative that is equal to 0 for a value of x. Definitely it's at a certain value of x. Let's say our x is equal to a. So it's just like this, is equal to 0. So at a point where x is equal to a, let's say it is this point. All right, let's say at this point, this is where our x is equal to a. At the point of what? At the point of inflection. It will help us to determine from that point or before that point, before the value of x, at the point of inflection, before this side or after this side, for these values of x which are greater than a, or for these values of x which are less than a, it can help us to determine whether the graph is concave up. Remember, facing up like this, it is what? Concave up. All right? Concave up. When it is like this, concave what? Concave down. So from the value of x, when x is equal to at the point of inflection, from that point for values of x greater than a, for this shape that we have, I'm talking about this shape, we can see that our graph is what? Facing up, like this. So it is what? Concave up. So from here, we're talking about a graph which is what? Which is concave up for values of x, which is greater than a. For values of x less than a, this side, we are going to see that our graph is what? Facing down like this. So it is what? Concave down. It is concave down. Very, very important for you to note. At x is equal to a, that's our point of inflection from or before that point. That's where we can tell whether the graph is concave up or down. But we saw the turning point is what? To show us whether from the turning point the graph is increasing or not. It is an increase or it is a decrease. So those applications, you are going to use them in as much in your calculations. You must understand this part. So turning points for what? Increase or a decrease. The point of inflection, concave up or concave up or what? Or concave down. That is the condition that is very, very important. All right. So that is your cubic function, guys. From this, let us just have something here. How to draw or in actually to sketch this. All right. So let us just say sketching or drawing. Sketching the graph. All right, that's sketching the graph. of a cubic polynomial here, right? This is M. All right, how to sketch this? We need the points that can help us. So in actual sense, what we are going to need, what is important from what we saw there, it is the x-intercepts, the y-intercept. All right, so we're gonna need x-intercepts. All right, the y-intercept. Okay, we also have the turning points and the point of what? The point of inflection. The turning points and the point of what? Inflection. Those are the main aspects. Those are the main aspects when sketching what? When sketching the cubic polynomial. All right. So that's the major part that you're going to actually need. All right. And I talked about the shape. So from that, f of x is equal to ax cubed plus bx squared plus cx plus d. A represents or gives us what? The shape. A is for the shape. So that is going to be for the shape. We talked about this. From here, when a is greater than 0, when a is what? Less than 0, that is for the shape. So you're going to need that in terms of the shape to know. Then you are going to need the x-intercepts, all right? For the x-intercepts, we do understand that y is equal to 0. So it's on a condition where f of x is equal to what? Where f of x is equal to 0. So for this condition, where f of x is equal to 0, you are supposed to apply the factor theorem in order to find the x-intercept. So you need to solve for what? To solve for x. You must solve for x when f of x is equal to what? When f of x is equal to 0. So that's apply what we had before, apply factor theorem, apply your factor theorem with the methods that we referred before. So on that factor theorem, it is either you're going to apply the long division in your factorization. All right, you are either going to apply that or the synthetic division, or by what? By inspection, which is our algebraic method. By what? By inspection. All right, by what? Inspection. So I have discussed these three methods separately. So use any one of what? Of the three to find the x-intercepts as you are solving for what? As you are solving for x, you're taking your f of x to be equal to 0. So the factorization part has to be done from any one of these, all right? So that is for the x-intercepts. You're going to need what? The y-intercept. So the y-intercept is on a condition where x is equal to what? When x is equal to 0. So simply the value of y will be equal to what? Will be equal to d. So that is the condition of the y-intercept, all right? So this is actually number 3. So that is what you're going to need. And as of the turning points, the first derivative gives us the slope of the graph to find the coordinates of the stationary points or the turning points. Thus, the first derivative must be equal to 0 when you consider what? The turning points. All right, so for turning points, I'm just going to write in short for turning what? For turning points, we are going to consider that the first derivative with respect to x is equal to what? Is equal to 0. So thus you can solve for x, meaning to say if there are two turning points, you're going to have two values of x, all right? So from this, you must solve for x, all right? So for x, substitute those x values into f of x to obtain what? The y values. You're talking about a point, remember? So that's the condition about the turning point, you can use the first derivative in order for you to determine what your turning points. There are so many ways actually, guys, that we can have that turning point. All right, if we are to consider the turning point, this and that, and I said it is used now in terms of the graph to say, is the graph increasing or what? Is from the what? The turning point concept. But that part we're gonna explain later on. All right. Then number 5, we are going to need what? The point of what? Inflection. So to find the coordinate of the point of inflection, we use the second derivative. All right. So for the what? The point of inflection, all right, we are going to use the second derivative. It follows that at that point, the second derivative is supposed to be equal to 0. So that's, you have formed an equation where you can solve for what? Where you can solve for x just like before, then substitute that value of x into the original function to have the value of y. The point of inflection is the one that is going to help us to tell whether there is, or whether the graph is concave up or down. All right, that's an aspect which is on its own this part of what being concave up and so on. So let me just list these ones because we talked about the turning points here. We talked about the point of inflection. So let me just write this down. These are properties now of our derivatives from what we have. Properties, let me just write this down. Properties of what? Of derivatives. The properties that we can actually get from this information. All right. The first one is on the turning points. Like I said, the turning point is going to tell us, is it an increase or a decrease? So it follows that for the first derivative, all right, we're going to consider an increase in f of x or a decrease in f of x. All right. So that's for an increase, or a decrease, in what? In f of x. So this is obtained from the first derivative of that turning point. Remember, the turning point, for the first derivative to be equal to 0, you are at the turning point. But from that, you can tell now to say, is that an increase or not? So if the first derivative with respect to x is greater than 0, that's an increase. You're talking about, remember, the first derivative represents what? Represents gradient expression. It represents what? Gradient expression. So when you are given the positive, it means there's a positive gradient for those values. You're going to be obtaining what? Positive gradient. That's an increase in f of x. So this one is going to be an what? An increase in what? In f of x. All right. But if this first derivative with respect to x is less than 0, we are talking about a negative gradient for that f of x. So meaning to say our f of x is experiencing what? A decrease. So that's a decrease in what? In f of x. So that's the first property for an increase or a decrease. Then the second property is going to be whether the graph is concave up or concave down. That's when you have the second derivative. Remember, you are at the point of inflection. So here, it is a property from what? It is actually a property from the turning points. So the second property is from what? From the point of what? From the point of inflection. But we are not using it. We are talking from there. This one was from the turning point when the first derivative is equal to 0. But from there, points can be referred, whether it is greater than 0 or it is less than 0. So the point of inflection was taken from the second derivative, remember, being equal to 0. So from there, we can have values that are more than that 0 or less than that 0. So that is the condition of our point of inflection. So for the second derivative with respect to x to be greater than 0, remember the point of inflection helps us to know this condition, being concave up or down. So when you are using the derivatives and this occurs that you obtain a positive value for the second derivative, it means your graph is what is concave up, right? So for this, the graph is what is facing up. That is what concave up. All right. Then if it happens that the second derivative with respect to x for that same thing is less than 0 like this, it means our graph is going to be what? Our graph is going to be concave down. It will be facing down like this. So that is the condition. It will be concave down. So the second derivative is to tell us whether the graph is concave up or down. The first derivative, it's an increase or a decrease. So they are going to ask this part, right? They are going to ask this because it's part of your derivatives, remember. So they are going to add this information when they are asking you these questions about what? About the cubic polynomial. So it is not just about sketching to say, all right, I just need to know the turning point, then you sketch. You are not going to have a question like that, which is just going to give an f of x is sketch that. No, this is just helping us to know the properties. But after that, guys, these are supposed to be the major properties to be known in answering of your questions and anything that we have done before. Remember, we talked about a tangent to a curve. So all those, you need to consider all those properties in order for you to what? To answer a full question about what? About sketching of a cubic function. So here I have got this question. Let me just try to put it in between. Let's see, like this. All right. So this is the question that we could just gonna consider. We want to see with this information that we have, if we are able to answer everything about this question here, all right, with this information. That's a typical question now is going to be given as. So you use every aspect from what we have done, all right, every aspect. So let us consider this. They're saying here, f of x is equal to negative x cubed minus x squared plus x plus 10. All right. A, write down the coordinates of what? The y-intercept of f. All right, which is, I'm just going to say, okay, this one is easier because for the y-intercept, I do understand that x is equal to 0. So if x is equal to 0, I'm going to take what? The constant, which is d. All right, you understand that. All right, so no problem. No problem when x is equal to 0, so y is equal to 10. So that's a point, which is what? Which is 0, 10. Okay? Then B, show that 2, 0 is the only x-intercept. Show that it is the only x-intercept. So meaning to say you had to solve for the x values. By solving, you will see that it is only x is equal to 2 that you're going to have. Remember, the x-intercept in the what? In the x-axis. We are talking about a condition where we are in the x-axis. And that's a condition where y is equal to 0, where we are referring our f of x to be what? To be equal to 0. And that's a condition that we are supposed to solve by applying our factor theorem and use any one of these: long division, synthetic, or by what? By inspection, any one. You see, guys. So this is what we had here on B to show that. So we are given our f of x, right, as negative x cubed minus x squared plus x plus what? Plus 10. All right, let's start first because already they've told us that for this value of x, where x is what? Where x is 2, that's the only x-intercept. So guys, it simply means they have actually made our calculations to be easier in terms of determining the first factor, which is our first linear factor. All right, let's go back so that you understand me. Remember when you had this synthetic division, all those methods, we referred to the factor theorem for the value of k that you substitute to obtain what? To obtain a zero. So here it's already there. They've already done that for us because 2, 0, guys, it means when x is equal to 0, y is 0, f of what? F of x. This is the condition is equal to 0. When x is 0, so it means simply means f of 2 is equal to 0. Already you have that condition. So therefore, x minus 2 is a what? Is a factor. You already have that factor. So you're not going to try again here, guys. Okay, factors of 10, this plus or minus 1, plus or minus 2, plus or minus 5, plus or minus 10. You substitute. No. Yes, in case that you do not understand from the point like this, you are going to do that. And by trying those numbers, you're going to see that it is only a 2 which is giving you a 0 at the end if you substitute in place of x. It is a 2 that is going to give you a 0. So thus, in our condition, we have got that as what? Just like f of 2 is equal to minus 2 to the exponent of 3 minus 2 squared plus 2 plus 10 like that. That is the one that is going to give us what's going to be minus 8, minus 4, plus 12 like this. So this is minus 12 plus 12, which is what? Which is a 0. So that is the condition that I'm trying to say. But you're not going to do all these calculations because already they gave us that. You are given that point. So in order for you to prove that this point is the only x-intercept, it is from the factor of what? X minus 2, where you are supposed to factorize by using any of the methods that I referred before, long division, synthetic, or by what? Inspection. So as for me, guys, I was just going to apply by inspection, all right? So by what? Inspection method from our algebra, I'm going to take this f of x minus x cubed minus, I want to factorize here, all right, since I have the first factor, minus x squared plus x plus 10 is equal to the linear factor of x minus 2. Then I'm going to obtain the second bracket, which is of the quadratic factor ax squared plus bx plus what? Plus c, where I said the bx here is supposed to be what? We are supposed to find the value of b. We do not know that one. What we know is the part of the first term and the constant, all right? You simply take it, the first term, divide by what? First term. First term of the cubic to the first term in your linear factor, the bracket. So minus x cubed divided by x was going to give us minus x squared. So here I have minus x squared plus bx. For the constant, 10 and what? Negative 2. Constant to constant. So divide 10 divided by negative 2. That's negative what? Negative 5. So this is our quadratic expression that we were going to obtain, but we need to find the value of b from what? From x squared, from the terms in what? X squared. From x squared, you find what? You find the value of b. The terms in x squared of these two brackets was going to be x times bx, which is what? Bx squared. And minus 2 times minus x squared, which was going to be plus 2x squared equals to what? To the x squared of the cubic expression on our left-hand side, which is what? Negative x squared, like this. So for this, I can find the value of b by what? Equating the coefficients of x squared. B plus what? Plus 2 is supposed to give us what? -1. So what is the value of b? Take the 2 to the other side of the equation. It's going to be a -2 like that. So b is equal to -3 minus 2 minus 1 minus 2. That's what? That is going to give us a -3. So that's our value of b, meaning to say this is going to be x minus 2 into what? Minus x squared. B is what? -3. -3x minus 5 like this. So you're going to factor out this negative, which is common throughout. This is it, negative into x minus 2. By factoring out negative, this is going to be what? Positive x squared, positive 3x, positive 5 like this. Can this be factorized? That is the condition. Can this be factorized? Because this here is going to give us a 2. X minus 2 is equal to 0, so x is equal to 2. That's the solution. But what about this one? If we were to solve, can this be factorized first? Factors of 5, which will give us what? A positive 3. We do not have factors of 5, which will give us what? A positive 3. 5 and 1, minus 5 and minus 1. So we do not have a condition where we can add and obtain what? And obtain positive 3. So thus, it cannot be factorized, this part. It cannot be factorized. If we were going to solve this now from our quadratic equation, were we going to have real solutions now? That's the question. Because factorization has failed. What about the quadratic? If you are to solve using our quadratic formula, were we going to have real solutions? All right, we simply test this one from our discriminant b squared minus 4ac. I want you to see something. Your b is what? 3. 3 squared minus 4 times a, which is 1, times c, which is 5. It was going to be 3 squared minus 4 times 1 times 5 like this, which is what? In -11. So if your discriminant or your delta is a negative, all right, if our delta is less than 0, remember there is what? No solution there. We do not have real solutions from this. So this part that we are having here is what? No real solutions. There's no real solutions. We cannot have the value of x from there. So therefore, the only solution that was going to be obtained was going to be from x minus 2, because that, if you factorize that, you're going to equate to 0 minus into x minus 2 into x squared plus 3x plus 5 like this is equal to 0. So x is equal to 2 from this bracket, but this bracket x squared plus 3x plus 5, when it is equal to 0, there is no solution. So you can see that the only solution was going to be what? When x is equal to 2. So hence x minus 2, x is equal to 2 here is what? Is the only x-intercept. That is the condition of our question. So that's the condition here. So hence or therefore x is equal to 2, or the point, because when x is equal to 2, remember y is 0, the point 2, 0 is the only x-intercept. That is the only x-intercept. The point 2, 0, when x is equal to what? When x is equal to 2. The other part, as we saw, we do not have what? We do not have a solution from there. All right, so that is how you play around. That's how you play around these questions, guys. All right. Then C, calculate the coordinates of the turning points of what? Of f. The coordinates of the turning points, which in our case for turning points, the first derivative has to be equal to what? To 0. The first derivative. So in our case, That is what you're going to consider from our f of x. Let us simply find what? The first derivative from there, then equate to 0. We are done. All right, so that is how you simply answer these typical questions, guys. Do not worry about do not worry much. Just do more revision on your side. All right. So that is it for C. For the turning points, we are going to consider the first derivative to be equal to 0. First derivative with respect to x is equal to what? All right. Drop the exponent. Remember, concept of the first derivative, you drop the exponent, subtract 1. All right. So if we drop the exponent, that's 3 times negative 1, negative 3x squared, subtract 1. So that's x squared. Drop the power, negative 2x is going to be x to the exponent of 1, which is x. All right. For a linear like this, you take the coefficient of x. It's a linear, remember? So the coefficient of x is 1. A constant, its derivative is what? A 0. You do not have anything that's plus 0 there. All right. So this is our first derivative. So we are simply saying this first derivative has to be equal to what? It has to be equal to 0. Then I can solve an equation that is being formed from this condition. So minus 3x squared minus 2x plus 1 has to be equal to 0 at the turning what? At the turning point. So let us try to solve this equation. You can use the quadratic formula or you can use the factorization. I can simply divide by negative, negative, negative. So that is going to be 3x squared plus 2x minus 1, all right, like this, is equal to 0. You can use your quadratic formula. You can use your factorization method, all right? There are so many ways, okay? But from that cheat method that's most of you said you want to work with, I said you're just going to take this, all right? The cheat method. All right, so just multiply by 3 here. 3 times negative 1, that is going to be negative 3. So that will be x squared plus 2x minus 3. Then you factorize this, considering factors of negative 3, which adds up to 2. That's 3 and what? Negative 1. So it's going to be x plus 3x minus 1. Then we bring back the x in place of what? I mean the 3 in place of x. So that is going to be 3 here, 3 here. In place of x, you put 3. In place of x, you put 3. So you factor out where we have got a common factor in these two brackets. 3 and 3 is common. So factor out 3. That was going to be x plus 1 into 3x minus 1. So these are the two brackets. This one is not important. Remember, it is useless. You do not take that. You take the brackets. These are the brackets that you're going to have. By any way of your factorization that you understand, you're going to obtain these two brackets, all right? So that is it. You have factorized this, or you have applied your quadratic formula, this and that. Remember, what you need is to solve for what? Is to solve for x, all right? So that is it. 1 to the other side is going to be a negative. Remember, two brackets concept equal to 0. So our x is going to be negative 1, or x is equal to what? Negative 1 to the other side is going to be a positive 1. Then you divide by what? You're going to divide by 3. Remember, 3x is equal to 1. Then divide by what? Divide by 3. So that is the condition. You have the values of x at the turning points. So thus, with these values, you can have the turning points. Remember, the question here is about the turning point. Calculate the coordinates. So to find now the value of y, you have to go back to the original function f of x. Substitute back there from f of x. Substitute these values. So from our f of x, which is given as minus x cubed. Remember, it was minus x cubed minus x squared plus x plus what? Plus 10. From that, when x is negative 1, that's f of negative 1, in place of x, put negative 1. So that's negative 1 to the exponent of 3, negative 1 squared plus negative 1 plus 10. You are going to obtain the value of y corresponding to that value of x at the what? at the turning point. So that is the condition at the what? At the turning point. All right. Let us see what we're gonna have here from our simplification. This was going to give us a positive what? A positive 9 from the value of x, all right, that I'm having. This was going to give us a positive 9. So when x is negative 1, all right, when x is negative 1, y is equal to 9. Here, remember, you need to what? Find the y values in this case. So when x is negative 1, y is positive 9. It's a point representing what? The turning point. So meaning to say there is a turning point that is given from this, all right? Negative 1 for the value of x. Y is what? Y is equal to 9. It's a turning point. The same thing for the value of x when it is equal to what? A third, 1 over 3. You're going to do the same f of what? 1 over 3. In place of x, simply put 1 over 3. So it was going to be like this, cubed minus 1 over 3 squared plus 1 over 3 plus what? Plus 10. So that was the condition. Simply put 1 over 3 this time. That's going to be 1 over 3 here. All right, let us see this one. 1 over 3 again. Okay, here it's 1 over 3. So that is the condition. That was going to give us 10 and 5 over 27, which is the same as 275 over what? 27. So it is the same as 275 over 27, like that. All right. So that's for the value of x. We are finding what? The y values. We have got another turning point for the value of x, which is what? 1 over 3. The y value corresponding there was what? 275 over what? 27. That's another turning point. So this graph that we are talking about has got two turning points. We have got what? Two turning points. So I'm going to write these turning points. All right, just like that, guys. First derivative for turning point, just use what? The first derivative, all right? So we obtained our turning points. Remember, our turning points, where can I write this? All right, I can just write it here. All right. That was part C, our turning points. Our turning points. Remember, we obtained the first one when x is negative 1, y was what? 9. And the second one, a third, when x is 1 over 3. When x is 1 over 3, y is 275 over 27. All right. Let us have that one again. That's the second turning point for 1 over 3. Y is going to give us 275 over what? Over 27. All right, so that was it. The first derivative has to be equal to 0 for turning points. Then you solve for x. Since you've formed an equation to say this is equal to 0, you solve for x the way that you understand, guys. But after that, substitute the values of x into f of x to obtain what? The corresponding y values for those turning points. All right, let us move on to the other part of our question here. Sketch the graph of f, show all intercepts with axes and all turning points. Then after determine the point of inflection was not necessary for this one. You see, they want you to determine it at point E after sketching the graph. So you just work out the way that you're given, guys. You work out the way that you're given. All right, let us try to have our sketch here. With the information that we have, what can we, what are we going to end up with? What are we going to end up with? That's D, all right? So that's our D here. Remember, our f of x is given with a negative on that, negative x cubed minus x squared plus x plus what? Plus 10, all right? So first, we had to consider the shape. A represents the shape, remember, in order for you to sketch this graph of a cubic polynomial. A represents the shape, the coefficient of what? Of x cubed. So that is for the shape. So we have to consider that from what we had here. Remember, if A is greater than 0, gonna have your shape like that, right? So our graph has got two turning points. All right, remember, it has got two turning points. The turning points that we have here, there are two. We've got two turning points. We've got what? Two turning points. Our A, the coefficient of x cubed is a -1. A is less than 0 and having two turning points. A is less than 0 and having what? Two turning points. This is the shape that you must have. Two turning points. Remember, this one and this one being our turning points. These are two turning points. Here it is one turning point. Here, no turning point. Remember the condition. Here, two turning points. One turning point here, no turning point on this one. So where we have got two turning points and A is less than 0, the shape is going to be like this. All right. So this is the shape that you were going to have in our case. So guys, you are supposed to be very, very careful in your presentation. All right. So our shape is going to be like this with two turning points, turning point, turning point. All right. So that is for the shape. But we saw that our graph has got one x-intercept at 2, 0. That's the only x-intercept. Remember, our x-intercept is only one. Our x-intercept. It's only one x-intercept that you have where x is equal to what? To 2. So on our sketch, with this information that we have, it is actually enough, guys, for us to have what? To have a sketch, right? Let me just try and just put something here that we can use to have our sketch at the end. All right, so let us say this is our y axis, all right, and this is our x-axis. All right, this is a sketch, guys. All right, this is just a sketch. So this is x here, this is y here, and that's our origin at 0. So we're going to have values, all right, from there 0, 1, 2, and so on and so on. So 1, but at 2, that's where we've got x-intercept 1, 2, 3, and so on. -1, -1, -2, and so on. Then the y values and so on. The is y-intercept at what? At 10. So that's, let's say this is 5, this is 10, this is 15, 20, and so on, -5, -10. So the 10 is important as it is our y-intercept. So according to the information, the x-intercept is only 1 at x is equal to 2. So you mark that. That's your x-intercept. The graph is going to pass through that. So if our graph was going to pass through, and remember the shape, this. So what about the turning points now? The turning points, we've got 1 in the negative at -1 versus 9. 9 is actually just below what? Just below 10. And this one, 275 over 27 is same as 10,1, something like that, right? That's 10,2. So approximately to 10,19 to 2 days, approximately something like that, 10,19. So it is above 10, just a little bit above 10, the turning point. Remember, at 0, 10, it's a turning point. So this one is just 10,12, just above that, approximately just a small, just a smaller portion from that. You have a turning point. And for a value of x, which is a third, guys, a third is it's closer to 0 then, closer to 0. So you're going to see that there is a turning point just above 10. There's a turning point. Then at -1 versus 9, somewhere here, there is a turning point. So remember the shape. So our graph is supposed to be from the top like this. It has a turning point here, all right? Then it's supposed to go up to the y-intercept. Then a turning point here, then something like that. Something like that. Remember the shape. So you must have something like this to a turning point, to the y-intercept, then to the turning point. But you see now the value of 10, the y-intercept, and this 10,124 for this one. It's close, very, very close, guys. So your sketch, just try to have a smooth, a reasonable sketch. The issue here is about the shape, all right? The shape is the most important thing. So here it's gonna be at a turning point at 1, then it goes down to this at 2. Here, guys, it's not gonna make sense according to what I have. I'm just gonna change my point 2, all right? I'm just gonna change my point 2 and bring it closer, all right? These 2. I'm just gonna bring it here. All right, so that's a 2 there. All right, so this is it. The 2 is the x-intercept, remember? So we have a turning point. This one is a turning point at -1 versus 9. When x is -1, y is 9. It's a turning point, this one. That's a turning point at -1 versus 9 here. Then a turning point just after the y-intercept at 10. Just after that, where x is what? A third, closer to 0, the closer to 0, where x is a third and y is 10,19, which is what? Which is 275 over 27. It's a turning point, this one again. It's a turning point. So this is going to be your sketch. That is the whole idea then. So you consider the shape, and we've got 2 turning points in our case. We've got what? 2 turning points. So it is like this. This one's a turning point. So you can have a better presentation than the one that I'm having here, guys. All right. So that's it. Your x-intercept at 2, the y-intercept at what? 10, the turning point, the shape. So it is not supposed to be accurate. The shape is important, and these points that we have indicated, that's our sketch. That's gonna be our sketch. All right. So that was it on part D. Then part E of our question is to determine the point of what? Inflection. So remember, in order for you to have the point of inflection, it's from the second derivative. The second derivative from our properties. All right. It's only that I did not mention. I mentioned here when sketching. For the point of inflection, the second derivative has to be exactly equal to 0. Exactly equal to 0. That is the condition of what? The point of inflection. So that is our point. That's E, to determine the point of inflection. So there you work with the second derivative to be equal to 0. Remember, when we determine the turning points, we had the first derivative. When we differentiated this, we got minus 3x squared minus 2x plus x. Remember, guys, we differentiated this when you're determining our turning points before here. We found the first derivative. When you're determining, it's only that I erased that. So it is just a continuation from that first derivative. All right, just continue from that first derivative. Do not start again to differentiate this. Yes, you can do that, but you already have your first derivative. So from there, continue, determine your second derivative. So you're going to drop the power, subtract 1. 2 times -3, that's -6x to the exponent of 1, which is simply minus 6x. For a linear term like this, the derivative is what? Is the constant -2. The derivative of a constant is what? It's 0. So that's nothing that you have. So this is your second derivative. But remember, you're saying our second derivative has to be equal to what? 0. So therefore, minus 6x minus 2 must be equal to 0. Then solve for x. You formed an equation. So you're solving for x at the what? At the point of inflection. That is it. So let's solve for x, guys. This is a linear equation. So simply add to both sides of your equation. This was going to give us minus 6x is equal to 0 plus 2. That's a 2. Divide by negative 6 to find the value of what? Of x. All right. So that is it. Our x is going to be positive to a negative. That's a negative. So that's negative 1 over 3. 2 into 2, that's 1 into 6. That's going to be a 3. So at the point of inflection, at the point of inflection, at the point of inflection, x is equal to minus a third. So what is the corresponding y value to obtain the point? Now, what we need is what? Is a point. So you have to substitute back to the original function, your f of x as given there when x is what? When x is minus a third. All right. So that is the condition. All right. So remember here we worked with a condition where x was a third, but this time it's minus a third. All right. So f of minus a third is simply going to be minus, in place of here, it's just going to be minus a third. All right, here, minus 1 over 3, a third, sorry, minus a third, minus 1 over 3 squared, plus minus 1 over 3 in place of x, plus what? Plus a 10. All right, so that was it. In place of x this time, you substitute that one as what? As minus a third, the value of x that you're having at the point of inflection. So that was the condition. Here I'm just going to put a negative, minus a third. All right, minus a third, minus a third, like this. So this is going to give us 9 and 16 over 27, all right? 9 and 16 over 27 for this value of x that we are having, which is, all right, here, let me check the question again. The question is determine the point. All right, so we have to, we need the y value again. So sometimes they can just say the value of x at the point of inflection, but in our case, we need the exact point. So this can be written as 259 over 27, 259 over 27. So therefore, our point of inflection is going to be given as x minus a third, and the y value 259 over what? Over 27. So this is the condition of our point of inflection from what? From the second derivative. You simply have to equate to 0. That is what you need to memorize or to go through to understand, actually, and understand this. You need to understand that. Work out as many questions as you can. So you see, this is just a basic question. I'm going to bring other questions, adding information to what we have, adding information to what we have. We're going to also need some additional notes on how to answer these type of graphs, to sketch, and also finding the equation of the cubic graph. So many other things that you're going to need. So just make sure that you follow the playlist that you have so that you can understand everything about your cubic function or the cubic polynomials, and also the derivatives. In application with our derivatives, we see that we have applications of what? Derivatives in answering these questions. So do not leave that part of your derivatives unattempted. Do understand each and every basic. All right, so that is it in basic. That is for you to sketch the cubic polynomial, this is what you're going to need. So simply work out more questions, all right, where you do not understand. If you have a question paper that you have been attempting and still difficult, you do not understand that, you can upload it on the community section, or you can talk about that, comment on the comment section, so that we can have a class based on that question, or based on those questions, all right? But for now, that is it. Till we meet again.